So before we move on to some actual algorithms, we will see two topics. One is growth of functions and asymptotic analysis. So asymptotic analysis is a way to analyze the running times of two algorithms and decide which one is the best. All right. So let's take a small example where the running times are T1n and T2n. And let's say T1n is something like, let's say, n square plus 3n plus 5, and T2n is, let's say, 100 times n plus 7. Now we want to figure out which algorithm is faster. Of course, the running time is dependent on the size of the input n. So let's have a look at how these functions behave with respect to n. For example, let's take n is equal to 10, and the first algorithm will run in 135 units of time, or that many steps, and T2 will run in 1007 steps. When n is equal to 100, this is 10305, and the second one is 10007. Then this is 1000. This is 1000 square plus 3000 plus 5. This is roughly a million, whereas this is roughly 100,000, that is 10 raised to 5. When it is 10 raised to 4, this is going to be roughly 10 to the 8, and this is going to be roughly 10 to the 6, so on and so forth. Now, if I want to know which algorithm is better, what I can say is, for n is equal to 10, clearly the first one is better. First one is faster. When n is equal to 100, both are roughly taking equal amount of steps. So what I can say is both algorithms are equally good. When it is 1000, clearly the second one is faster, almost 10 times faster. And in this case, this is almost 100 times faster. And if you try more numbers, you can see that the second one will continue to be the faster algorithm. To see this better, let me just plot a small picture with x-axis n, input size, and the y-axis is running time. And if I plot T1 and T2, T1 will look something like this. It's a quadratic function, T1n, and T2, in the beginning T2 is much higher than T1, so let me start from here, and this will grow linearly. So this is T2n, and both of these equations will meet when n is around 100. So this is around 100. Now what can I say about the running times of these algorithms with respect to the input size? When n is a small number, or when the input size is smaller than 100, clearly this algorithm is faster, that is the first algorithm. Whereas when n is more than 100, the second algorithm is faster. Right? So essentially for small values of n, the first one is faster, whereas for large values of n, the second algorithm is faster. So how should we decide which one is the best? Okay? Or in other words, which region is more critical, right? The speed of the algorithm in which region is more critical. And my claim is that we should focus more on this region, or we should give more importance to this region. One way to convince you is this. Look here. Here the input size is small, like 100, in that case, even the running times are also really small numbers, like 100, 1000, 10,000. These are really small numbers for a computer nowadays, right? So you may have two algorithms where one algorithm takes, let's say, 1 second, and you have the second algorithm which is, let's say, 100 times faster, which can do the job in, let's say, 10 milliseconds, right? So 1 second versus 10 milliseconds, that's what is happening here. In some sense, both these algorithms are, performing okay. I mean, they can do the job in some decent time. But now when it comes here, you may have two algorithms where one algorithm is faster than the other one. Maybe let's say 10 times faster. But this n is so big, then the actual running times are also going to be so big. Then what could happen is maybe one algorithm will take, let's say, 1 day to finish the job, whereas the other algorithm will take maybe 10 days or 100 days to finish the job. So 100 days is too much, right? For any real life application, we don't want to wait for 100 days, but 1 day is probably okay, we can live with it. Right? So whether an algorithm is really useful or whether it is practical or not, that real check is happening here when n is extremely large. Right? So which means we should worry about, or we should really focus more on the speed or the running time or the performance of these algorithms for large values of n, and choose the best which has better performance in this region. And this sort of analysis is called asymptotic analysis. So essentially in asymptotic analysis, we simply assume n tends to infinity. So just assume that n is a very, very, very large number, and then have a look at these running times and find the one which has the lower running time. So that is what is asymptotic analysis in a nutshell. Now let's have a look at these functions again in the asymptotic sense. That is, n is very large or n tends to infinity. When n tends to infinity, you can see that these small numbers like 5, 7, these are pretty much irrelevant. Also, there is n square here, there is 3n. So this n square is going to be a much, much larger number compared to 3n. So in some sense, 3n will have very negligible effect on the total time. So we can even ignore 3n. Okay, so only this term will survive. Similarly, only this term will survive in the second function. And what are these terms? These are nothing but the dominating terms. Okay, so at this point I want to kind of introduce what is known as the big O notation. Big O notation, very informally. I'll introduce now in an informal way, and we will see it in more detail later. So in big O notation, what we can do is we can say that T1 is big O of n square. So simply you find the dominating term, and if there are any constants in front of it, just ignore it, and you can write it as, the first one you can write as big O of n square. The second one, have a look at the dominating term. In this case, this is 100n. Ignore the constant, so you have only n left. Then we write this as big O of n. Okay, so this is kind of an informal way of defining big O. And now let's see what is the actual proper definition of big O. Alright, so let's continue with big O of n. What I have written here is three functions. The first one is 3n square plus some other terms. Second one is 1000 n square plus n raised to 1.5. The third one is 8 times n raised to 1.999 plus n log n. And what I'm claiming here is, in asymptotic sense, all of these can be written as big O of n square. Let's see if this is in line with our informal definition before. Obviously, the first one is fine. The dominating term is n square, so I can write it as big O of n square. For the second one, again, you agree with me that that is n square. For the last one, if you look here, the dominating term is n raised to 1.999. So obviously I can write it as big O of 1.999. And what I have written here is, I wrote it as big O of n square. So what is really happening here? And this is correct, okay? And there is nothing wrong in writing this one also as big O of n square. So can we take a clue from here and give a proper definition of big O? Yeah. So big O means, or big O of n square, specifically big O of n square means, it's the set of all functions. It's a set of all functions. There can be infinitely many functions such that their dominating term is either n square or it is dominated by n square. That's my definition. So the dominating term of these functions must be either n square. In this case, this is n square, so we are fine. Or it should be something such that it is dominated by n square. So it is n to the 1.999 is clearly dominated by n square. So this is true. If I had another function, let's say n log n, again n square dominates n log n. So this also I can write it as big O of n square. But can I write something like n cube as big O of n square? No. Can I write something as n to the 2.001 as big O of n square? No, because n to the 2.001 is not dominated by n square, right? So we can kind of say that this is the set of all functions with the dominating term is either n square or it is dominated by n square. Okay, there was still a specific example. So just for the illustration, this is a set of all such functions. N log n can be here, n can be here, a constant, let's say 5 can be here, log n can be here, log n can be here, but n to the 4 cannot be here, 2 raised to n cannot be here, etc. Right? So what is the formal definition of big O? Formal definition of big O of f of n is this. Big O of f of n is a set of all functions g of n, such that f of n, such that when n tends to infinity, f of n and g of n are the same, right? Or the dominating term of g of n is equal to f of n, or the dominating term of g of n is dominated by f of n. Okay, which means when n tends to infinity, limit n tends to infinity, what is g of n by f of n? When the dominating term of g of n is equal to f of n, what will happen is when this grows to infinity, this will converge to a constant, a non-zero constant, right? A non-zero constant. And the other scenario where the dominating term of g of n is dominated by f of n, what will happen is this term will converge to 0, which is still a constant. That means it is 0, right? So that is one way to define big O of f of n. It's essentially the set of all functions such that limit n tends to infinity, g of n divided by f of n converges to a constant, which can be either a non-zero constant or just 0. Both are fine with us. For example, in this case, when g of n is this thing, this will converge to 3. Whereas in all the other example like n log n, n, 5, log n, log n, in all these cases, this will converge to 0. So that is one way to define big O of f of n. Another way to define is, if you don't want to use these limits and all those things, is g of n such that, set of all functions such that there exists a constant, c and a number n0 such that g of n is always less than or equal to c times f of n for all values of n greater than n0. This is another way to define g of n. It simply means beyond some point, that is n0, g of n is bounded by some constant times f of n. That means f of n is always ahead of g of n, right? This c is just to just to take care of the constants in front of both functions. But once you ignore these constants, after some point, g of f of n is going to give a bigger value than g of n. That's the definition of, this is f of n. That's the definition of big O. And you see here that big O denotes a set. So that means whenever we have a function like this, we should use the notation. We should use this notation. 3 times n square plus 9n plus 4 belongs to big O of n square. Again, this belongs to big O of n square, etc. This is the right way to use big O. But typically, or almost all the time, we use equal to, instead of a set notation, we use equal to, which is just for convenience. In math, we call it as what? Abuse of notation. So we know that it is technically slightly incorrect, but it's okay. That is more convenient to use. And this is all about big O. There are 4 more, standard notations, which we will see next. Alright, so we have already seen what is big O. Big O of f of n is set of all g of n's such that g of n over f of n tends to a constant, and the constant can be 0 or non-zero. That is big O. Now what I want to show is small o. Small o of f of n is again the set of all functions g of n with limit n tends to infinity, g of n divided by f of n. We want this to be a constant again, and that constant must be 0. That is called small o of f of n. The next thing is big O of omega. I'll show examples for each of this. Big O of omega of f of n is nothing but, this is actually the inverse of big O. Big O and big omega. Big omega is the inverse of big O. For example, big omega of f of n is a set of all functions g of n, set of all functions g of n such that when I say the inverse, I'm going to write it in the opposite way. Limit n tends to infinity, f of n divided by g of n is equal to a constant. Constant which can be 0 or non-zero. And similarly we have small omega. The same thing, g of n and limit n tends to infinity, f of n divided by g of n. Again we want this to be a constant and it must be 0. And the last thing is called theta, which is theta of f of n is a set of all functions g of n such that limit n tends to infinity, f of n over g of n, or even we can write it as g of n over f of n. Let me just write it as f of n over g of n. That should be a constant and it cannot be 0. These are the 5 standard notations we will see in this course, and oftentimes we will be playing with big O. So in some sense, big O of f of n is kind of giving an upper bound, something like a equivalent to a less than or equal to. Small o is something like I'm giving a bound, and what is on the left hand side is strictly lesser than what is on the right hand side. This is just the opposite scenario, greater than or equal to. This is strictly greater than, and this is similar to equal to. Just to make it more clear, I will show some examples. So big O of, let's make a specific example. Big O of n square means the set of all functions such that that function on top and n square on bottom, and this quantity will tend to a constant when n tends to infinity. Constant can be a normal, constant could be even 0. So that means this is functions like 3n square plus 2n. Okay, the dominating term can be n squared, or it can be 1.99, or it can be n, it can be log n, etc. But you cannot have n cube here. When it is small o of n square, we can have all of these functions except those with n square as dominating term. So we just want to avoid n square. Anything below n square is fine, strictly below n square. So we can have n, we can have n to the 1.5, we can have n log n, we can have n raised to 1.999999, but we cannot have n square is not allowed here. Okay, n square or any constant multiplied by n square is not allowed here. So now here, that is omega of n square means the set of all functions which are, with the dominating term is either n square or more than n square. So you can have things like 3n square plus 5 is totally fine here. We can have n cube, we can have n raised to 5, we can have 2 raised to n, we can have n factorial, but we cannot have n here. We cannot have log n, right? So we want everything above n square. We cannot have n raised to 1.99999. That's not allowed here. That is big omega of n square, and small omega of n square is similar. You can have all of these things except those functions with dominating term n square. Okay, so we need to just avoid these things. So we can have n to the 4 is fine, n to the 2.00001 is fine, but n square is not okay. And lastly, this is kind of like equal to, and this is called theta. Theta of n square basically means the set of all functions whose dominating term is equal to n square. So, n square plus 3n plus 9, or even if you have a constant in front of this, that's okay. But you cannot have n cube now. You cannot have n raised to 2.001 now. You cannot have n square log n, etc. All the functions whose dominating term is strictly n square. So that is why it is roughly equal to. So one thing you can see from here is if somebody says that f of n is equal to big O of g of n, and I'll just so these are some easy inequalities which you can come up with, or easy relations you can come up with. So if somebody says that f of n is equal to big O of g of n, you can immediately say g of n is equal to big omega of f of n. And this relation works both ways. So that means if somebody gives you this, you can say that is true. And this is true for small omega, small o and small omega. Okay, that is, if somebody tells you that this is true, then you can immediately say that g of n is this. And another thing you can say is, if somebody says you theta of g of n, what you can immediately say is f of n is equal to big O of g of n, and g of n is equal to big O of f of n. Or even you can say that f of n is big omega of g of n, and g of n is big omega of f of n. So all of these are some of the easy corollaries you can get out of the actual definition. And one thing we need to keep in mind is big O is usually used for for showing upper bounds. Right? Once we give an algorithm, we want to kind of say that, okay, the complexity is big O. So big O is almost like giving you a guarantee, right? It is almost like telling you that, okay, here is my algorithm. The running time is bounded by n square, right? And if n square gets evaluated to some number, let's say, I don't know, 5 hours, that means my algorithm is guaranteed to be completed within 5 hours. It could be 4 hours, 3 hours, 2 hours, but never more than 5 hours. I mean, that's what we want to know when we actually try to execute an algorithm, right? So that way we can plan the next thing. So that's about big O. And sometimes we can even give it in terms of theta. So that is kind of telling you that, look, my algorithm is going to take 5 hours, you know, right? Not more, not less. And omega, this omega thing is usually used to represent what is called lower bounds. And if you remember, lower bounds are for problems, not for an algorithm. For a specific problem, there might be some inherent bottlenecks, which makes it hard to solve it, you know, faster than some point. So in that case, we say that, okay, look, this algorithm has a lower bound of n log n. For example, comparison-based sorting has a lower bound of n log n, which we will see soon. That means nobody can come up with an algorithm better than n log n, right? So that is kind of telling you that, okay, you can try all the tricks, but this is where it is. And if you ask me why is the lower bounds useful, one explanation is this. Sometimes we have a problem and many people try to come up with better and better and better algorithms. And suppose if you know the lower bound, right? Suppose if you know the lower bound, once we get an upper bound that is matching with the lower bound, we can stop working on that problem, right? Because we know that there is no point in working hard to get a better algorithm, because that is impossible, right? So usually in this kind of research, we want to study problems from both sides. We want to come up with newer and newer algorithms that can give better time complexity. And we also want to understand what is the lower bound. So that way, you know, once we match this upper bound, once we establish an upper bound and we get an algorithm that can match with that upper bound, then we are done. Then we can stop working. So that is pretty much all the notation. So I think we can jump into some real algorithm problems. So maybe I need to show one last thing, that is some of the high school stuffs which you might have forgot. So I'll just refresh few more things and we'll move on to some sorting algorithms. Alright, so this is a quick recap of some of the high school materials. What's the sum of numbers from 1 to n? 1, 2, 2, 3, etc. up to n. This is equal to, there are n terms, and the average value of a 10 is what? 1 plus n over 2. So the total sum is n into n plus 1 by 2. This is actually big O of n square. What about this? How to sum up something like this? 1 plus 1 over 2 plus 1 over 4 plus etc. up to, let's say, infinity. What we can do here is we can call a name for this, that is s, and you can write this as 1 plus half into s, which means 2 times s is equal to 2 plus s, or s is equal to 2. In general, when you have something like this is 1 plus r square plus etc., where r is strictly less than 1, you can write this as 1 plus r into s. Therefore, s is nothing but 1 divided by 1 minus r. We'll be using these kind of things very often. Now, what about this? 1 plus r square plus r raised to n, and in this case, r is more than 1. How to sum this thing? Again, what I can do here is, let me just take r raised to n outside and write these numbers in the reverse order. So what I will have is 1 plus 1 over r plus 1 over r square plus etc. Right? So this 1 over r is a number which is strictly smaller than 1. So that means, so this I can write as a constant. This I can write as a constant. So that means this entire thing is going to be a constant, or I can write as r raised to n. We perhaps may not need the actual sum. We just need all of these things in bigger terms only. And the last thing is harmonic series. I hope you remembered. Harmonic series you represent using Hn, that is 1 over 1 plus 1 over 2 plus 1 over 3 plus up to 1 over n. And if you remember, this can be written as roughly, so this is basically a sum, and sum can be approximated using an integral, nothing like 1 over x dx, where x goes from 1 to n, and you can approximate this as log of n, where log is to the base e. Yeah, so these are some of the sequence, some of the old tricks. Yeah, just remember them so that we can use it later. All right.